question means sequences and series is chapter 11 in the book. So we are just going to jump to sequences and series. And again, I'm trying to say why sequences and series. And I'm trying to explain to you the skip. The skip is because, you can integrate this, you can integrate this, but you can't still integrate this. So the technique of integration is, the idea is to write this function as a series and then to integrate it when it's written in terms of series. That's the only way you can find that integral. So in some ways we are talking about integration, but at the very end, it is because first you have to get acclimated or used to what a series is. And what a series is cannot be done without understanding what a sequence is. And that's where we are headed. So we're going to talk a lot about series, but in the end, we're going to tie it up because we want to ultimately, what we want to do is we want to integrate. So it is still an integration technique. Series are also useful in solving differential equations, which are, again, a relation between a function and its derivative. So having said that, let's start with sequences. So what are sequences? For me, sequences is just a list. It is a list of terms. Well, what kind of terms? And a lot of notation now. So I'm going to say it is A1, A2, A3, A4, and so on and so forth. So how long is this list? Well, infinitely long. So this goes on forever. And we are going to give the notation that A1 is the first term, A2 is the second term, A3 is the third term, and of course AN is the nth term of the sequence, and so on. So usually we write sequence using the notation AN, but when we use that notation, it is understood that n goes from 1 to infinity, meaning and n is just an integer. Meaning when I write something like a bn, for example, n goes from 1 to infinity, usually skip that. We don't write that because we understand that when we use this is the set notation. So in some ways, sequences is a set. It's a collection of objects. So then we understand that this bn is really b1, b2, b3, b4, and so on and so forth. So let me just give some examples. So can you write this sequence for me? So either type it or say it. So this sequence would be
1 over 1, 1 over 2, 1 over 3, etc.
There you go, sir. So in other words, what I just did that with that example is this was the sequence, really. This was the list. But I sort of wrote it in the condensed form. In other words, I gave you a formula for the nth term. Because remember, the notation says you're supposed to write an. I'm just saying I wrote an as 1 over n. And what I gave you there is formula for the nth term, and this is what we are after. And what does it mean, formula for the nth term? Oh, I'm just saying if n equals 1, then this part is, or maybe I should write it down here. So all I'm saying is I can generate, sorry. So I'm going to draw my boxes again. So this is formula for the nth term. And what does that mean? Oh, I can generate the entire sequence Well, how do I do that? And here it goes. So when n equals 1, I'm saying this is a1, and the term is 1. When n equals 2, it is a2, the term is half. N equals 3, it is a3, the term is a third, and so on and so forth. So one of the things is that given a sequence, you should be able to find an, which is really the formula or the nth term of the sequence. And what do I mean by that? Here we go. I'm going to give you two examples. So we are interested in two kinds of sequences. And you must have seen those before. Number one, we're going to look at the arithmetic sequence. And number two, we're going to look at the geometric sequence. So question so far. Are you writing with me? Do we need to pause, or we are okay?
I'm fine.
So, some indication from you? Okay. So you're keeping up writing with me then, Russell? Is that?
Yep.
Okay. What about the rest of you? Okay. Great, but feel free to interrupt and ask me any questions if you have. So what is the arithmetic sequence? So I'm going to give you a general formula, and then you're going to do this for me. So arithmetic sequence is made up of these kind of numbers. You have a plus d, a plus 2d, a plus 3d, and so on and so forth, where this is the first term and d is the common difference. So what do I mean by common difference? So it seems d is the difference if you take the next term minus the previous term. So this is your first term, this is the second term. I should say maybe we want to call it B1, B2, this is B3, this is B4. All I'm saying is take any term in this sequence. If you take B4 minus B3, the difference will be D. If you take B25 minus B24, the difference is going to be D. If you take B2 minus B1, the difference is going to be D. And that is what is called the common difference. And so I'm just going to say that can you tell me then, just looking at it, just guessing here. So B1 is A, B2 is A plus D, B3 is A plus 2D. So can you tell me what would the nth term would be? Just looking at the pattern. So I just want you to look at the pattern. That if it is B1, then it seems it is A. If it is B2, it is A plus D. If it is B3, it is A plus 2D. So my question to you is, can you see this pattern? So if it is Bn, you're close, Sam, but pay attention. So Bn would be what? Sam, you're almost there. Look at the value of n. So this is what I'm trying to say. So if it is B1, can I say this is A plus 0 times D? If it's B2, it seems it is A plus 1 times D. If it is B3, it seems it is A plus 2 times D. So if it is Bn, it's going to be A plus... Go on, Sam, correct yourself. You almost had it there. There we go, Cecily. A plus n minus 1 times D. So there it is. So if you have arithmetic sequence, Amiu, now I'm going to answer yours. So here is an example. So here is the sequence. Here's the list. So tell me is this arithmetic sequence? So when I ask you this one, what are you going to check? You're going to check for two things, the common difference and the first term. So fill in these two for me. So A equals
1.
very good. And D equals
So I'm not quite sure how to write it. The pattern is a addition of 2 each time.
there we go. So you're just going to say, okay, 3 minus 1, because next minus the previous, and you're going to check if it's the same for everybody. And it looks like it's the same for everybody. So D seems to be, remember what is D? It is the next term minus the previous term. So I have drawn the arrows there. So you're going to check 3 minus 1.
And minus 2?
5 minus 3, 7 minus 5. So the common difference is 2, right?
Mm-hmm.
There we go. And so if I ask you, remember, what is this? This is the first term. This is the second term. This is the third term. The fourth term is 7. So if I ask you the nth term, you're going to use this formula. So you're going to say it is 1 plus n minus 1 times 2. So Bn is going to be 1 plus 2n minus 2, which is 2n minus 1. And now let me explain what I'm trying to say, and then I'll take questions. So what are you saying? You're saying this sequence that you wrote out there can be written as 2 minus n. Well, are you right? Are we right? And I'm just going to say, okay, if this is Bn, then when I put n equals 1 here, I should get B1. When I put it in this formula, I get 2 times 1 minus 1, which is 1. So it checks out. If n equals 2, I get B2, which is what? 2 times 2 minus 1, which is 3. So checks out. So I can indeed generate the terms of the sequence. Are we okay there?
Yep.
Are we all right? So this is the arithmetic sequence. And then we can have, I'm going to kind of go quickly through this. So the other kind of sequence we are interested in is the geometric sequence. And I like to do two of these together. So what is this geometric sequence? Oh, you should look for the first term. And you should look for common ratio. What was common difference again? You were saying if you take this difference of what? Next term minus the previous term, meaning what next term minus the previous term? B4 minus B3, B25 minus B24, B2 minus B1. Doesn't matter where you are in the sequence. I could say B101 minus B100. You will still get it to be D. And that's why the word common, the difference, because you're subtracting the terms. Having said that, tell me what would common ratio mean? So R would mean what? Instead of subtracting, now you're
Dividing?
doing what? Very good. So you're dividing. So you're dividing what? Next term over the previous term. If you don't like this, I'm just going to say, this is my general way of writing it. So I'm just going to check for the common difference, which is B2 over B1 the same as B25 over B24? Is it the same as B100 over B99? That is what I'm talking about. So I'm taking the ratio, which means I'm dividing, but I'm dividing what? The 100th term divided by the 99th term. The next term, which is the 25th term, divided by the previous term, which is 24th. B2, which is the next term, divided by the previous term. So that is how I would write it. So if you want to change this phrasing to something that was more simpler, more better than this, go for it. But that is what I'm saying. So it's the next term over the previous term, which is R. So it should be common, meaning when I take this ratio, all of them should give me the same number. That's called common ratio. If you have such kind of a sequence, it's called a geometric sequence. And I'm going to write a general form of the geometric sequence first, and then I'm going to throw numbers in there. So far so good. No questions there. I'm just going to keep asking because this is going to move fast. The sequences part is going to move fast, and we're going to get into series. But you have to grasp the concept of sequence to get the concept of series. And that's why I'm asking what I'm asking.
I mean, we're just talking about patterns, right?
Yeah. Right now, we're just talking about patterns. We're just talking about this list, but it's going to get a little bit. I'm going to segue into the next one very, very quickly. So here we go. So I don't see any questions. So here is the geometric sequence. So I can say that the first term is r. The second term is r squared, r cubed. So can I say here that the common ratio is r? The first term, which is the first term, is r. Do we agree? Now let's put some numbers in there. So what could be examples of this geometric sequence? So I'm just saying if r equals 1, then can you tell me what this sequence looks like? If r equals 1, what does this sequence look like?
One squared, one cubed, 1 to the 4th.
Very good. So in other words, it's just a list of ones. Leave some space there because we are going to come and talk about, there you go, Lucas, thank you. If r equals 2, now what does it look like?
Oh, it's the same. 2 squared, 2 to the 3rd, etc.
2 cubed, 2 to the 4th, and so on and so forth. Example 3. If r equals half, what does it look like?
1/2 squared, 1/2 cubed.
And the last one, I guess, if r equals -2, what does it look like?
Wouldn't that look the same at, no, r, it'd be -2, -2 squared, etc.
Now we're going to get to what Amir is saying. So here is a list. How long is this list? Infinitely long. What do we want to know? We want to know eventually, and I'm going to write it colloquially, and then you are going to turn it into math. So here we go. So here are the 4 sequences. They are all geometric sequences for right now. So you want to know eventually. Sorry. Eventually. What happens to the terms in this list? Let me rephrase that. I'm asking if I follow these terms, if I follow this list to infinity, what happens to the terms? How do the terms behave? I promised you a rephrase, so here we go. So then I want to know, how do these terms behave? If I want to answer these 2 questions, what am I talking about mathematically? Remember, what was the list again? Oh, it was A1, A2, A3. You had some AN somewhere, and it was infinity. So I'm saying if I want to follow this list together, then I want to know what happens eventually to those terms, to those individual terms. What happens to them? So what mathematical thing am I talking about? What mathematical concept am I talking about? That I want to know what? I want to know the behavior of these terms as they go to infinity, which means we are talking about what? There we go, Sam. So we are talking about, if you want to answer this question, eventually what happens, then you are supposed to take limit as n approaches infinity of an. Why an? Because an is the nth term of the sequence. So now tell me, if this limit is a finite number, then we will say what? The sequence eventually converges, right? If this limit is infinite, or it does not exist, then we are going to say that this sequence diverges. This shouldn't surprise you. You did this in chapter 8, because you said if the value of the integral is infinity, that means what? It's going nowhere. Or it does not exist. Then it diverges. And if it approaches a finite number, then it converges. So what are we interested in? We are interested in if the sequences converge or diverge. So we are interested in, does a sequence converge or diverge? So if I have to answer this question, I'm going to put it in a box. Then what do? Number one, I need to find an. What is an? The formula for the nth term of the sequence. Then I need to take limit. N approaches infinity of an. At this point, I want you to understand that I'm relying on your calculus 1 finding limits, which is L'Hopital's rule, but really you're going to look at finding limit as n approaches infinity of something. And once you find that limit, what are you saying? If this limit that you found up there, if this is a finite number, you will say the sequence converges. If this limit is infinite or does not exist, you're going to say the sequence diverges. So I want to go up there and I want to know what happened to those 4 examples. Does the sequence converge or diverge? So questions, are we ready? So far so good? Because you have to understand the concept again. What's given to you? List. How many terms again? Infinitely many terms. So you just want to know the behavior. As you follow to infinity, what happens there? Does it end somewhere? Does it go to a particular number? And so on and so forth. That's what we're looking for. So I just want to know if you are ready. These are the 3 things that we're going to do, and we're going to see which one converges or which one diverges.
Yes, I'm ready.
Okay, so let's go all the way back and let's start with my example 1. So what do you think? What is an first of here? Remember, what is n? N is just the nth term. So you look at your sequence. This is your sequence. This is your list. Can you tell me what the nth term would be in this list?
1.
There we go, sir. And what is limit n approaches infinity of 1?
I mean, that's not a limit, is it? It'd just be 1 or 0?
It is 1. Because again, you have to understand it both conceptually and mathematically. That you're saying what? If I follow this list of 1s to eternity, what will I end up with eventually? What is the behavior? The behavior is all of them are one. So nothing is changing there. They're just one. So this is just one. So if you want a visual of this one, then I'm going to say this, and I want everybody to stop writing and just look at this one. This is how I like to treat sequences as. So when I'm saying to you that this is one, I want you to visualize this. Christmas is far away, but it's coming. You are going to put up lights. So let's say you put up lights. This is y equals 1. You put up lights. And 1, this is 1. So I'm saying this is the first light, this is the second light bulb, this is the third light bulb, and they are all here. So I want you to imagine this 1 as those light bulbs. So no, the wire doesn't bother us because it's not about the wire. It's just about those light bulbs that you hang in there. So your third light bulb, your fourth light bulb, sorry. Oh, jeez. So your fourth one, and then fifth one, and sixth one, and so on. So let's say you've got this Christmas lights that you're putting up, and it's really long, they're eternity. But you've put them at one level, isn't it? It's just a y equals 1. So if you follow them to eternity, how are the light bulbs going to look like? They're going to look the same. It's 1. But mathematically, we're going to say this sequence converges. What does it converge to? It converges to 1. Are we okay there? So what are sequences? The bulbs on the Christmas light, people. And you are going to look at this one right here. So tell me, what is AN here? The first term is 2. The second term is 2 squared. The third term is 2 cubed. The fourth term is 2 to the 4th. So the nth term would be, very good, Cecily, 2 to the n. So we want to know whether this converges or diverges. So we take the limit as n approaches infinity of 2 to the n. And for this one, I want you to think of Christmas lights again. So I'm saying 2 to the n. Isn't that this exponential function 2 to the x? But then what are these terms? Aren't they just 2, 4, 8? So I'm just following the Christmas lights, the red lights. And can you tell me eventually what's happening to those red lights? So as n approaches infinity, 2 to the n approaches, the limiting value is, very good, infinity. And so what happens to this sequence, this 2 to the n? It diverges. What does that mean? The terms just keep on increasing. They don't approach any number. They don't stop. It just grows exponentially. How do I know? Because I know that this term that you're talking about are just Christmas lights on this wire, which is 2 to the x. Are we okay there? So I hope this Christmas lights analogy is going well, but let's look at the next one then. So I want AN here. Again, A1 is half, A2 is 1 over 2 squared, A3 is 1 over 2 cubed. So AN is going to be, there we go, 1 over 2 to the n. So I want to know what happens eventually, which is 1 over 2 to the n. Can I write this as limit n approaches infinity 2 to the negative n? And so what is this function then? What is the limit here? Very good, it approaches 0. Because what is this one? Isn't it this exponential function? Because what are your lights now? Oh, aren't they half? And then a quarter, and then an eighth, then a 16th. Well, what's happening to them? Oh, they are approaching 0. So does this sequence converge? Yes, this sequence converges. or you can write half to the n. It's the same thing. So this sequence then converges. Think about the next one. What about this? So an is what to begin with? So again, pointing out to you that a1 is -2, a2 is -2 squared, a3 is -2 to the cube. There we go. So it is -2 to the n. So I want to know limit as n approaches infinity of -2 to the n. Think about this one and tell me what the limit is and why. And look at the individual terms. Pay attention to the individual terms of the sequence. That is your light bulbs. And what about them? So if you try to plot them as we did before, what happens? Very good, Sam. And why do you say it does not exist? Very nice, William. So I'm just going to say that if you look at those terms of the sequence, if you just draw a picture of them, what happens? You have -2, then you have -2 squared, which is 4. Remember, 1 corresponds to the first term. So I'm saying 1 corresponds to the first term, so this is a1. 2 corresponds to the second term, so which is here. 3 corresponds to the third term, but which is down here because it's -8. And the next one is going to go up there. The next one is going to go down here. So what happens eventually, if you follow this to infinity, what happens? It keeps bobbing up, isn't it? It's up or down. So mathematically, I'm going to say that if n is even, then it seems you have a positive number, positive large. If n is odd, then you have a negative. You're saying you're going to follow to eternity. Okay, but you're going to tell me where you stop. So if n is even, then you're stopping at somewhere here. If n is odd, then you're down here in the depths. So here, this limit does not exist. And what does that mean? Oh, this sequence then diverges. Having said that, I want you to answer this question. Then what about this sequence then? What about this one? So what is limit as n approaches infinity to n-1? What about this one? Converges or diverges? What is the limit there? Very good. The limit is infinity. And so this one, very good, Joshua, this one diverges. So obviously, what are we interested in? We are interested in the sequence that converge. And I'm going to just give a quick one. So from this geometric sequence, this one that I did, I found out something. And what did I find out? I'm just looking at, and this is my fourth comment here, that the geometric sequence, and this is there in the book. So if you want, you can look up in the book. I'm trying to, but I have a different edition anyways. So I'm just trying to write it there. So the geometric sequence, the sequence R to the n, this is convergent if -1 is less than r, is less than or equal to 1, and it diverges for all other values of r. Where is this coming from? I want you to refer to our examples 1 through 4. But then we have to go to something else. So let me take you to one example that I particularly like, which is going to be, I wanted to get into series today, but it's not happening. But don't worry, the homework, do as much as you can, leave the series out. So here we go. Here's the next part. And here's an example, which you will see in the homework today. So I want to determine whether this sequence converges. And I'm just going to take an example from the book. And this is going to be determine whether this converges or diverges. I'm going to write a solution to this one. For this entire chapter 11, whenever you see a sequence or series, number one, you're going to write out the first few terms. I want you to get a feel for that sequence. So here we go. So the first terms is 1 over, the second is 1 over 2 to the squared, 1 plus 2 over 3 to the cube, and so on and so forth. So it seems like this is 3 to the 1. This is 3 squared. Sorry, 2 squared, my bad. So this is 2 squared. This is 2/3 is about 0.6, so I'm just going to write this is 1.06 cubed, and so on and so forth. So first thing, this is just my observation. Is this a geometric sequence then?
Yes.
And when you say yes, look at what the geometric sequence was. What was a geometric sequence? You would take this over this, you would take this over this, and it should give you a constant. It should give you a common ratio. So is it a geometric sequence? And the answer would be no, it's not a geometric sequence, right? Meaning you can't use this. Because if it was a geometric sequence, I could tell you just by this theorem whether it converges or diverges. So very good, Sam. It's neither. It's not geometric. It's not arithmetic. Because there's no common difference. There's nothing of that sort. That means what? If I want to answer this question, converges or diverges, I just have to take this limit. The question is, how do I compute this limit? Oh, I have to use L'Hopital's. But before that, I have to also use ln. So this is from last semester. So I'm going to call on some people. You know who you are. You should know how to do this. And that's going to be Trent, Long, Nara, Russell. We did this last semester. So
oh, you really got to call me out like that, huh? All right, let me get my notes from last semester.
Because you were not saying you're not too ready to talk to me now after we switched to online. You don't like me anymore, so I had to.
Oh my God, no! I was gonna ask you because I had my advising meeting today, and I was going to ask you if you knew if you were like teaching a section of Calc 3.
Oh, you're a brave woman. So.
Yes, I am.
No, I don't know because nobody's even thinking about scheduling right now.
Oh, really?
So, yeah, so I have no idea what I'm teaching next semester.
Okay.
Yeah. So, here we go. So, all of you should know this. So, we want to find limit of this one. So, we're going to call it y. So, I want limit n approaches infinity of am because this is an. Let me stick to that. So, I'm just going to say this is what I want. But an is 1 plus 2 over n to the n, so I'm going to call it y. And I want to know the limit of y. But to know this limit of y, I'm going to erase this. I'm doing too many things here. I'm just going to box this. This is what I want. I want the limit of this one. So I want to find limit n approaches infinity of y, which is y is this. So to find this limit, I'm going to take ln of both sides. So I get ln of y equals n ln of 1 plus 2 over n. I'll be okay with that.
Yes.
And I just
Yeah.
use the log properties. Nera, Russell, Long, and Trent, all I want to hear from you is a yes. That goes for Jiwoo as well.
I already got my yes in there.
Okay. So, in other words, I am going to just Lucas. I forgot you. I'm so sorry. I apologize, Lucas. That's the other person. So these people don't even talk to me. There's got to be yes there. The others, I'll be more kinder to you. But these 5 people, 6 people, they are not getting any kindness from me because they should just know this flat out. So here we go. So we are going to go to this one. So we take limit now. ln of y is going to be limit as n approaches infinity n ln of 1 plus 2 over n. So I'm going to say this is of the form infinity times 0, which is the indeterminate form. I want my 5 yeses.
Yeah.
Yep.
There we go. And so what do we do then? We go limit as n approaches infinity, ln of 1 over 2, 1 over n. This is the move we make when we use L'Hopital. So now this is of the indeterminate form 0 over 0. Right?
Yep.
There we go. I'm just looking at the time and I'm just going to run through this and I'll take questions whoever wants to stay behind. So here we go then. We are using L'Hopitals. So this becomes limit as n approaches infinity. Remember, we are taking the derivative of the numerator times the derivative of the denominator. Remember, the derivative of this one is negative 1 over n squared. I'm just taking care of the algebra here. And so these cancel. I'm going to say as n approaches infinity, I want 5 answers here. 2 over n approaches
Infinity. Right? The bottom gets larger and larger, so 0.
There you go. So it approaches 0. So you have limit as n approaches infinity of ln of an to be 2. So now we are saying ln of limit as n approaches infinity of an is 2. So if ln of something is 2, then that thing must be e squared. Again, you've seen this. So the 5 people, you should be very comfortable with this one now. You should be giggling and chuckling and smiling because we were face to face when we did this. So this sequence converges or diverges?
Converges.
Very good. So this, because the limit is a finite number. So this sequence converges. So I'm going to stop right now, but here is a thing for all of you. The homework is going to involve series because I thought that I would go through the series and show you some fun things today. So do as much as you can. And the other questions you can ask me on Friday. It's due Friday midnight anyway. So you should be able to do some of it. Most of it actually. And just the last couple, 3 or 4 problems, just hold off on them when you see series because we haven't gone over series. So these are kind of my office hours right now. So I know Cecily has chemistry to go to. Nera probably has chemistry after. Russell, I don't know about you. Are you still in chemistry or not?
I am still in chemistry.